So, good morning, everyone. This is Yasir along with Azizul and Sajjad. We are presenting our project of hate and offensive speech detection in Bengali language using the machine learning and the deep learning techniques. And in these days, social media makes it really easy to connect and share ideas, but at the same time, it also makes it easier for hate and abusive comments to spread. If this kind of content is not detected early, it can create misunderstandings, increase negativity, and make online spaces feel unsafe. Since manually checking everything is very slow and does not scale well, the automatic detection systems are becoming more necessary. In addition, working with Bengali language adds extra difficulty in compared to the English language. That is because Bengali has a fewer high quality labeled datasets and modern NLP resources, so it is often treated as a low resource language. In our project, we have treated this as a multi-class classification problem. That means for each Bengali comment, our model predicts one of the five categories, which is gender abusive, geopolitical, personal, political, and religious. We chose these five because they represent common types of harmful content, and they are not all the same. For example, a personal insult is different from a religious hate comment, so the system should be able to separate them instead of calling every word as toxic, like the same toxic level. And if we look at the figure one, it shows the overall pipeline. We start with the label data, do pre-processing and normalizing the text, split the data set and into training and testing sets using stratification, handle classes imbalance on the training side, and then train multiple deep learning models and then like the using accuracy as well as macro average metrics, which are more fair when classes are imbalanced. So our main contributions are: we built a complete hate and offensive speech detection workflow which is easy to follow and repeat. And we have compared 8 models in a fair setup, which are recurrent models like simple RNN, LSTM, GRU, including their bidirectional versions, and also the transformer based models like the BanglaBERT base and BanglaBERT large. And since the dataset is not balanced across classes, we focused on macro precision, recall, and F1 score. And we also used the confusion matrix to see where the models get confused. And in terms of related work, earlier Bengali hate speech research mostly used traditional machine learning models because the strong pre-trained Bengali models were not much available. And in the recent studies show that like the transformer based models in Bengali focused ones like BanglaBERT are much better at understanding the context and handling the spelling variations compared to traditional models. And another important direction is explainability, which means making the system decisions easier for humans to understand, which is important for trust and the fair moderation. So overall, our goal is not only to get good scores, but also to build something that would actually make sense in real moderation settings. That's why we were very careful with the train and test separation, the handling the imbalances properly, and used metrics that reflect even minority class performance too. With that, and I will be handing my flute to Azizul, who will explain the dataset, pre-processing, and the training setups. Thank you very much.
Hi, I am Azul Kubijat. I will explain our dataset, pre-processing steps, and the models and training configuration we used. In terms of dataset, we use a publicly available Bengali hate and offensive speech dataset, which contains 3,411 labeled comments. Each comment belongs to one of five classes: gender abusive, geopolitical, personal, political, or religious. In figure 2 of the report, um, the report, we include a small snapshot just to illustrate what real level entries look like. You can see that the language is informal and resembles typical Facebook or YouTube comments, which is exactly the environment we want our system to handle. In terms of pre-processing, Bengali social media text is noisy, so we apply standard cleaning before training. This include removing URLs and other noises. In the code, we can see that we removed extra white space and control characters, URLs, numbers, emojis, Bengali and English punctuation. Uh, these elements can sometimes carry sentiment, but in our baseline setup, we remove them to reduce sparsity and keep the models focused on textual patterns. Um, then in terms of train test split and imbalance handling, we split the data into 80% training and 20% testing using a stratification, meaning class properties are preserved across the split. However, the dataset is still imbalanced. In the figure 3 shows the class distribution in the held out test set. Some classes have much lower support than others. To reduce bias towards majority classes, we apply random oversampling only on the training data. Here we can see that random sampling is only used on the training data. This helps the model see minority class examples more often during training while keeping the test set untouched, so the evaluation stays realistic. In terms of model, we evaluate 8 deep learning architecture. Uh, we used simple RNN, LSTM, GRU, and their bidirectional versions. Bidirectional RNN, bidirectional LSTM, and bidirectional GRU. For these models, we use a word level tokenizer with a fixed sequence length of 15 tokens. We choose 15 uh, as a practical length for short social comments. It keeps a computation small while still capturing the core meaning for many samples. Each comment becomes a sequence of token IDs. Then we pad or truncate to length 50. Here we can see the tokenization and uh, tokenization and padding process. We use an embedding layer initialized with 300-dimensional Bengali group vectors. Uh, here we can see that the Bangla group embedding code. Uh, and we keep this embedding layer frozen. Freezing reduces overfitting on a small dataset and provides a stable semantic starting point for the RNNs. Later we used transformer models such as BanglaBERT base and BanglaBERT large. Here we use the official BanglaBERT tokenizer and set official BanglaBERT tokenizer uh, and set maximum sequence length to 128. So the model can the model can retain more context from longer comments. Unlike static embeddings, BanglaBERT produces contextual representations, meaning the same word can be interpreted differently depending on surrounding words. Uh, in terms of training setup for RNN models, we train for 20 epochs using the Adam optimizer with learning rate 0.001, and we keep 10% validation split from the oversampled training set to monitor learning. For the BanglaBERT model, mm, we fine-tune for three books using an Adam W-style optimizer schedule with smaller batch sizes to fit memory constraints. After training, we evaluate the accuracy and macro average precision recall and F1, which our member 3 will discuss in the results section.
Hi everyone, I'm Sajjad Hussain Pappu. And now I'm going to cover the evaluation matrix, our results, and the main takeaways from the error analysis and conclusion. In the evaluation part, we report accuracy because it's easy to interpret, but accuracy alone can be misleading for imbalanced datasets. So we also report macro averaged precision, recall, and F1 score. Macro means we compute the metric per class and then average. So minority classes matter just as much as majority classes. In addition, we use a confusion matrix to see which specific categories the model confuses. In the result part, table 1 contains the main numbers among the RNN baselines. Simple RNN performs the worst with accuracy of 32.46%, accuracy and 0.42 macro F1. By RNN is slightly better but still low. LSTM improves to 51.32% accuracy with 0.50 macro F1, and by LSTM improves further to 57.01% accuracy and the 0.549 macro F1. The strongest RN family is GRU. Standard GRU reaches 67.54 accuracy and zero point 0.601 macro F1, while by GRU is close with 65.20% accuracy and the same 0.601 macro F1. Overall, gated RNN is clearly handle this problem better than a plain recurrent layer. So why is simple RNN is so weak here? One reason is the vanishing gradient problem. Simple RNN struggles to preserve information across longer sequences, reducing its ability to learn context dependent cues. Also, our RNN setup uses a fixed sequence length of 50 tokens and static word level embeddings. If a comment is longer, truncation can remove key context, and static embeddings cannot adapt well to spelling noise or morphological variations in Bengali. So generalization suffers. Transfer models performs best. BanglaBERT base achieves 80.85% accuracy with macro precision, 0.675 macro recall, 0.790, and macro F1 0 and macro F1 you can see is 0.776. BanglaBERT large is slightly lower, 79.9% accuracy and 0.758 macro F1. A reasonable interpretation is that the large model has higher capacity, but with limited level data, it can be harder to fine tune effectively without instability or overfitting. In figure 5 and 6, uh, in visualizes these differences. Figure 5 compares macro precision, recall, and effort across models, and figure 6 compares accuracy. Both plots show a clear progression. Simple RNN at the bottom, LSTM by LSTM mid-range, GRU the best RNN baseline, and the BanglaBERT models at the top. uh, in this future work uh, part, we can say our data set is relatively small and may not cover all dialects. spelling styles, or code mixed content, random oversampling duplicates training examples, which can increase overfitting. Future work could explore data augmentation, class weighted loss functions, and stronger evaluation like cross validation and cross domain testing. Another useful direction is explainability, so moderators can see evidence for why a comment was flagged. In the conclusion part, uh, transformers fine tuning, especially BanglaBERT based sustainability, outperforms RNN baselines for Bengali multi-class hate and offensive speech detection, achieving the best balance of accuracy and macro F1. So thank you for listening. The presentation. I stop the presentation here.